Today I'll be presenting an experiment to verify Snell's law and also an experiment to verify a lateral shift, which is seen through the refraction of light. Snell was a Dutch astronomer and mathematician, and he found the equation, Snell's law, in 1621. And he didn't actually know how great his discovery was. He died before others found just how impactful Snell's law was. So here we have Snell's law, and it states that the sine of the incident angle, which is this angle here, between the incident ray and the normal line, the dotted line is the normal line. So this angle between these two lines is the incident angle, which will be used for the sine of the incident angle times the index of refraction for the first material here, N1. Light is traveling through this material. Multiply that by the sine of the incident angle is equal to the sine of the refracted angle. Here's the refracted angle between the refracted ray and the normal line. Sine of the refracted angle multiplied by the index of refraction for our second material, N2. Now, the index of refraction, N, is equal to the speed of light in a vacuum divided by the velocity of the light in that material. So it's different for each material depending on how fast the light can travel through it. So here's our normal line, the dotted line. If the light is slowing down when it enters this second material, if it's slowing down, the refracted ray will be closer to the normal line. If the light speeds up in the second material, the refracted ray will be away from the normal line. The two materials we're going to be using today are air and glass. The light will be traveling from the air first and then into the glass. So N1 is the air and N2 is glass. When looking up the index of refraction for glass, a typical piece of glass would have an index of refraction of 1.50. This is found on physics.umd.edu. So to verify Snell's law, we'll use this piece of glass, which is a tile piece. You can see through the glass here. And we'll use this to find the index of refraction for the piece of glass. First, we're going to outline the glass piece on both sides so we know exactly where to put it back, which we'll come to in a second. And we're going to draw on our normal line. Okay, once we have our normal line, we'll line it up again this way and choose an angle. I'm going to choose an angle of 20 degrees here. Connect that to where the normal line intersects at where the glass piece will be. And this will be our incident angle. Now to find our refracted angle, first we're going to I have some pins. I'm going to put that in our incident angle at various distances. It doesn't really matter where they're at. They want to be straight up and down. Then we're going to put our glass piece back so it's right where it was before. Now we're going to come down to the side, and you can see that through the glass, the image of the pin is not directly where the actual pin is. So we're going to scoot over until they're right in line. See how they come together right there. What I've done is put two pins in line with the two here. There's a little bit of a glare, but they're here. If we come this way, we've put the 2 new pins in line with the image of the 2 pins on the other side. So now we can remove the glass. Since we have our 2 pin set, we can remove the pins. Our little dots here where the pins were, we'll use that to draw our line. And that is where the light ray is exiting. Now to find our refracted ray and our refracted angle, we'll take this point and connect them. And this is our refracted angle. Now that we have our refracted angle here, we can take our protractor and measure that angle, 13 degrees, right here. So our incident angle we chose to be 20 degrees, and our refracted angle we found to be 13 degrees. Now, the index of refraction for N1, the medium here is air, and we know that the index of refraction for air is 1. So in our equation, sine of the index of refraction N1 equals the sine of the refracted angle times the index of refraction for our second material, the glass. We know that this is 1, so we will rearrange to find N2, and it will just be the sine incident angle over the sine of the refracted angle. So our index of refraction for our second material, N2, is 1.52 with no dimensions. Index of refraction has no units. The expected value for the index of refraction of the glass was 1.50. The calculated measurement that we got for the index of refraction of the glass was 1.52. So in the calculations, there's a little bit of error, and it was 2/100ths off of the expected value. So those findings are pretty concisive that Snell's law is in fact true. Now we're going to take a look at a lateral shift, which occurs with a refraction. Now a lateral shift is where the incident ray coming in is, if you keep that line going, is perpendicular to the ray coming out of the glass. So we're going to start by drawing our second normal line for our exiting. And now we're going to make a right angle here with this. And this right here is the distance of our lateral shift between those 2 lines. A lateral shift is equal to T, the thickness of the glass, this way, T, over the cosine of the refracted angle multiplied by sine of the incident angle minus the refracted angle. I'm going to be using the millimeter ruler on my protractor to measure the lateral shift. The lateral shift is 9 millimeters. So our expected shift equals 9 millimeters. Now we can measure T, which is 72 millimeters here. So T equals 72 millimeters. And we have the refracted angle and the incident angle already. So we'll just plug this in and see what our calculated lateral shift is. So our calculated shift equals 9.005 millimeters. Something I wanted to point out about the lateral shift in our diagram here, with this being the incident angle and this being the refracted angle. With the lateral shift, what it is when this angle, when this ray exits the piece of glass, if I turn this upside down, this is the same 20 degrees as the original incident angle when it started. So the lateral shift is this ray coming out at the exact same angle as the incident ray. It's just been scooted over a little bit from the original path that the ray was headed.